What design weaknesses caused the Space Shuttle Challenger disaster? Imagine being part of a space mission that ends in tragedy just seconds after launch. What went wrong? Today, we look into the design flaws that led to the Challenger disaster. The main issue was with the rubber seals called O-rings in the joints of the right solid rocket booster. These seals were supposed to keep hot gases from escaping during ignition and flight. But the design made them vulnerable under certain conditions, especially when it was cold. On the day of the launch, temperatures were unusually low. Cold weather made the O-rings stiff and less elastic. When they should have sealed tightly, they instead failed to do so. This delay in sealing allowed hot gases to leak past the primary O-ring. This leak is called blow-by. Over time, the secondary O-ring was eroded by the hot gases. The erosion caused a breach in the booster joint, and hot gases escaped into the surrounding area. This hot gas ate through the metal casing of the booster, causing it to break apart. The destruction of the booster then led to the explosion of the entire shuttle. This design flaw was known before the disaster. Engineers had seen damage to the O-rings on earlier flights. They noticed erosion and blow-by, but the problem was not fixed. The design included a backup O-ring and some asbestos putty to prevent leaks, but these measures were not enough in cold weather. The failure to improve or test the seals for low temperatures was a serious oversight. Beyond the O-rings, the overall shuttle design had other weaknesses. The crew cabin was right next to the boosters, so a failure in the boosters could directly threaten the crew. The shuttle program also lacked a good risk analysis. Management decisions from the Apollo era focused more on cost and schedule than safety. This led to accepting higher risks, like using boosters with known issues and not having a proper escape system for the crew. Organizational problems also played a role. Engineers warned about the O-rings' performance in cold weather, but their concerns were ignored or downplayed. Decision-makers pushed to keep the launch schedule, even with known safety issues. This breakdown in safety culture allowed the flawed design to be used under unsafe conditions. In short, the Challenger disaster was caused by a design flaw in the O-rings that failed in cold weather, combined with poor testing, risk management, and organizational decisions. It shows how a small component's weakness, if not addressed properly, can lead to a major catastrophe. It highlights the importance of designing for all conditions, fixing known issues, and listening to safety concerns before launching.